Welcome to the motion of charged particles in an electric field, part 3. So today, in this lesson, we're going to look at charged particles moving at an angle to a uniform electric field, and we're going to talk about coming in 90 degrees to a field at an angle, vertical, and a couple of different angles like that. So it's very similar to projectile motion ultimately, but we're talking about electric fields now and charged particles rather than masses in gravitational fields. First example is if you think of a particle as having an initial velocity and it enters a field through a hole in that plate. So if I've got my parallel plate here, I put a tiny little hole in it and I throw a charged particle into it. So in this case, it's a charged particle. We know that the charge goes from positive to negative. It's going to come whizzing in. It's going to be fought against that field, so it'll slow down. It may touch, it may not, but then it's going to stop, and then it's going to come back again. So that's basically exactly the same as this example here. Whereas if I throw a ball straight up, it's fighting the gravitational field. So it goes up, slows down, stops, then starts to accelerate back down towards where it wants to be. So it's no different to this gravitational situation. So here, I throw my particle in, and I would say that it's initially moving anti-parallel to the field, because remember, it's opposite to the direction of the field lines. So last lesson we talked about this acceleration formula, and you need to be able to derive that from Newton's second law, and it tells you that the acceleration of an object is the electric field strength times the charge of the object times the mass, divided by the mass of the object. So it's inversely proportional to the mass. So this is exactly the same situation between these two as the ball being thrown against a gravitational field versus a charged particle being fired into an electric field. So we can use the electric field strength, the acceleration, and those equations of motion to calculate things like how long does it take this particle to stop, how long will it take it to return back to the original plate or back through the same hole, and how far will it travel before the final velocity is zero. So at what point in this field does it get to before it's actually stopped? If a charge is projected horizontally, or perpendicular to the field, then it's going to be pushed or pulled from its initial position as it travels through the field. Just like you throwing a ball horizontally in a gravitational field, it's pulled downwards toward the earth. So we would call this a deflection, or we could call it a displacement as well. Just like if you throw a ball horizontally across the air, it's pulled downwards by gravity. So you could say how far is the ball deflected from the horizontal to the ground by the time it hits. In this case, if I was to stand on a building and you were to stand down on the ground and I threw horizontally and you caught it, I could calculate, well, how much has it deflected from my height to your height in the time that we measured, in this case, for the ball to actually get to you. So we're doing the exact same thing here with the electric field. We're saying I throw or fire a charged particle across an electric field, so it's perpendicular to it, and it's going to be deflected either up or down depending on the charge. And if I measure the distance, so if this was its original trajectory and it's pulled downwards by this distance, this difference here between what it was traveling, like the direction it was traveling, and where it ended up is its deflection, or sometimes we'll just call it the displacement. It's the same thing. One thing to know is that just like in projectile motion, the path is always parabolic. So it's not just going to do this weird jagged straight line. It always creates a parabolic style path. Given the field acts only vertically in this case with my parallel plates, and there is no acceleration in the horizontal motion, that tells me that the speed that it's traveling horizontally to the right in this case is not going to change. So I can say that the horizontal velocity is just the distance divided by time, and therefore I can rearrange that for time and say that the time it takes is just the distance it travels divided by the speed it was traveling. In this case, the distance traveled, we would use L to symbolize it's the length of the field or length of the parallel plate that we're traveling through. And we divide it by V0, which is the original speed it was traveling. And assuming that we haven't actually hit the plate or it's been stopped, the V final is going to equal V0 anyway. It's a constant velocity in the horizontal direction because we're assuming an isolated system, and also there is no electric field horizontally to slow it down. It's only being deflected in one direction. So have a go at this problem here. You're given the electric field magnitude, and they're applying a potential difference across the plates to do that. they throw in this particle on the right, which is a negative particle, and it's an electron. So that's great. We know its charge, we know its speed. It's fired in at 2.5 times 10 to the 7 meters per second. And you know the length of the plates L is 0.125 meters. So calculate the time of flight for the electron through the electric field based on the equations that we've just talked about. Okay, if you need a little bit more time, feel free to pause it. I'm going to reveal the answer for you, but it's just using that the velocity is distance over time, therefore time is distance divided by velocity. We know that L is 0.125 and the V we were given, so I compare the two things and I get my 5 times 10 to the minus 9 seconds. So that's how long it took to travel across the field. Okay, again, these are some worked examples. So the time of flight is already given to you and the magnitude and direction of the acceleration of the proton are given to you because we've already done that stuff. So that's not important at this point. Now I want you to talk about in part C, what is the path that it's going to take? Draw it, sketch it in your notebook or just visualize it in your head. Calculate the magnitude of its vertical displacement. So that's that deflection we've talked about. Calculate the magnitude of the velocity and give its direction, because they've just said calculate velocity, not magnitude, as it leaves the electric field. So what is it doing when it leaves the electric field? Okay, so I'm going to reveal the answers to this. If you need more time, just pause it now. Otherwise, these are the solutions. So you can see here in part C, it's coming, it's a negative charge and it's attracted to the positive plate. So it's going to deflect upwards. Then they've said calculate the magnitude of its displacement. In this case, we knew enough information that we can use the distance it's displaced by because I knew its acceleration upwards and I knew the time that it was traveling for. So it was displaced by 4.61 times 10 to the negative 2 meters. Then calculate its velocity. Its velocity has to be a vector equation. I knew what it was originally traveling and I've calculated its change in velocity upwards. So I have to Pythag this to figure out what is the resultant velocity. So it needs to be vectorially done. Then you can also use Pythag to get the direction, and it's deflected by 36.5 degrees above the horizontal. So that is your angle of deflection. Earlier in topic 1, we looked at a projectile initially being launched at an angle to the gravitational field, just like the picture on the left. So if we throw a ball up, we know that it follows this parabolic path before it gets back to the ground. If we replace this object with a charge and we replace gravity with a uniform electric field, we have exactly the same sort of scenario, and it looks a bit like this. So if I have this small gap in my electric field and I fire a charge into it, it also follows a parabolic field, because remember that this is identical to an object moving through a gravitational field. So using this concept, have a go at this kind of question. I've got an object that is fired downwards 30 degrees from the horizontal. It's in an electric field, it's a negative charge, so it's going to be attracted to the upper plate. So it's going to follow some sort of parabolic path. Whether it hits the plate or whether it gets out the other side, we don't know yet, but we can calculate that. So find the magnitude and horizontal component of the initial velocity. So far that's just a projectile motion style question, but it's upside down. Rather than being above the horizontal, it's below the horizontal. Then calculate the vertical component, show that the electron does not strike the bottom plate. So they want you to show how much it'll displace before it comes back up. show that that is not equal to 5 centimeters, basically, in this case. If it's 5 centimeters or more, well, it can't be more, but if it's 5 centimeters, it slams into that plate. And then show that the electron spends 5.76 times 10 to the minus 9 seconds in that electric field.
Some people dream success. Don't let your dreams be dreams. You should get to the point where anyone else will quit, and you're not going to stop there. So just do it. Make your dreams come true. Do it. Nothing is impossible. Do it. Make your dreams come true. Yes, you can. Yes, you can. Just do it. Don't let your dreams be dreams. Yesterday you said tomorrow. Yesterday you said tomorrow. Yesterday you said no. You're gonna wake up and work hard at. You're gonna wake up and stop giving up. You're gonna wake up and work hard at. You're gonna wake up and make your dreams come true. Don't let your dreams be dreams. What are you waiting for? Yesterday you said tomorrow. Yesterday you said tomorrow. Yesterday you said no. You're gonna wake up and work hard at. You're gonna wake up and stop giving up. You're gonna wake up and work hard at. You're gonna wake up and wake up. Just do it. Make your dreams come true. Do it. Nothing is impossible. Do it. Make your dreams come true. Yes, you can. Yes, you can. Just do it. Do it. Just do it. Do it. Just do it. Just do it. Nothing is impossible.
Okay, so hopefully you've had enough time to get through these questions. I'm going to put the answers up now. If you need more time, as always, just pause, keep going through it, have a go at it before I show you the answers. So in this case, they've used v cos theta, just like in projectile motion, to get the horizontal component. Vertical component is then v sine theta. Show that it does not strike the bottom plate. In this case, we want to show that the distance is not the 5 seconds, it's less than that. So we want to know what S is. I know everything else. I rearrange because I know my initial vertical. I know the acceleration in the opposite direction. And I get that it's 0.0212 meters. So the distance between the midpoint of the plates and the bottom plate is 5 centimeters, which we talked about. It only undergoes a vertical displacement of 2.12 centimeters. So it does not strike the plate because it doesn't get to the full 5 centimeters. Then show that the electron spends this amount of time in an electric field. Velocity is distance over time. In this case, I'm talking about horizontal components. So distance horizontal is 0.125. It's the length of the plate. I divide it by the horizontal velocity, and I get 5.76 times 10 to the minus 9 seconds. So that confirms what I wanted. Hey, we're back. Okay. So this is an application. I'm going to show you a video shortly, and hopefully I'll be able to put together a demonstration for you guys in a classroom. But this is a Teltron tube. So a Teltron tube is a device that is designed to basically show you the deflection of an object in an electric field. So what happens is a small current heats the filament, which in turn releases electrons. So these heated filament gives off electrons. And electrons, as we know, have this charge. So they're therefore then pass through accelerating plates. So you've got these plates that accelerate it, gives it speed. The filament and the accelerating plates are what we call the electron gun. So this component here is the piece that generates the electrons, and then it accelerates them, it fires them across this field. So this is my electron gun. It sounds a lot cooler than it is. It's just the thing that generates high-speed electrons. Once I've got this, my electron gun then shoots them into a uniform electric field. And as we've talked about before, we would expect the thing to deflect. So if you've got these parallel conducting plates and I'm shooting an electron between them, it's going to curve or deflect or follow some sort of this parabolic path. We could put a grid within the tube. A lot of them will have this grid pattern, and we can use this to actually measure the deflection by using the grid pattern. We can calculate things like the strength of the electric field, the charge of the electron, all this kind of stuff. So it's a physical application to confirm all of these concepts to do with the electric fields.
The Teltron tube. The Teltron tube is an apparatus which can be used to demonstrate how electrons behave in a magnetic field amongst other things. It is made of an evacuated glass bulb which contains a small amount of hydrogen or argon gas. The second part is an electron gun. On the electron gun a wire is placed with marks that have a space of 2 cm between each other in this case. The Teltron tube is placed between Helmholtz coils. A simplified drawing of the electron gun is showed here. In the upper left is a wire or spiral to which a voltage UH is applied. The resulting current causes the wire to heat up and it begins to glow. At the same time electrons are emitted. Due to the emission of electrons, the wire is called hot cathode. On the opposite, a metal plate is placed with a hole in the middle, which is the anode. To the anode and the hot cathode a voltage is applied which leads to the electrons being accelerated into the direction of the positively charged anode. The higher the voltage is, the faster the electrons become. While most of the electrons hit the surface of the anode, some fly through the hole. To focus the beam, a so-called Venel cylinder is placed between the hot cathode and the anode. It is connected in a way that a voltage can be applied, causing it to be negatively charged in comparison to the hot cathode. The electrons are repelled by the cylinder and moved to the opening, which leads to a more fine and brighter beam. In my case it didn't work properly, so it wasn't used in the experiment. In reality the experiment looks like this. First, the voltage at the hot cathode is increased. Then the voltage between the hot cathode and the anode is increased until the beam becomes visible. Some electrons hit the gas molecules, which causes them to glow. Then the Helmholtz coils were connected, which produce a uniform magnetic field. By increasing the current, the strength of the field is also increased.
Okay, so questions for today's lesson. Page 157. 12 to 16 has questions about what we've talked about. So question 12 is a horizontal projection style. Question 13 is also horizontal projection, but we've got a proton now. So we've gone from a negative charge to a positive charge, but it's the same style of question. 14 gives you an angled projection into a field, which includes calculating the field. So it gives you some more practice on calculating those electric fields, and then you're actually measuring the projection of an angled particle. 15 is very similar, it's more angled projection style, and then 16 is questions involving the Teltron tube. It also includes some experimental questions, so that's a good little practice for some experimental stuff. Later on in the year we'll do an experimental test, so it's good to have a go at this. And part C is a bit of a challenging question, so have a look at that if you feel like a challenge.